You've been lied to. The speed of light isn't the cosmic speed limit you think it is. There are loopholes, exceptions, phenomena that laugh at the rules, and they're more common than you'd ever imagine. So here is a question. If you could travel at the speed of light without consequences, where in the universe would you explore? Let us know in the comments. I will pin the most creative answer. Now let's begin. Imagine you're an ant walking across the surface of a balloon. You can only walk so fast. That's your speed limit. But what happens when someone starts inflating the balloon? The surface itself expands. 2 points on opposite sides of the balloon move apart faster than you could ever walk between them. You didn't break any rules. The ground beneath you changed. That's essentially what's happening with our universe right now. Space itself is expanding. And here's where it gets wild. Distant galaxies aren't just moving away from us. Space between us and them is stretching. The farther away a galaxy is, the faster this expansion carries it away. Beyond a certain distance, galaxies recede from us faster than light could ever travel. This isn't theory, this is observation. The Hubble Space Telescope has been measuring this for decades. The James Webb Space Telescope, which began its mission in 2021, has given us even more precise measurements. In April 2026, just weeks ago, an international collaboration called the H0 Distance Network published the most accurate measurement of the universe's expansion rate to date. They found that space expands at approximately 73.5 kilometers per second for every megaparsec of distance. Let me break that down. A megaparsec is about 3.26 million light-years. So for every 3.26 million light-years of space between us and a distant galaxy, that galaxy appears to move away roughly 73.5 kilometers per second faster. Stack enough distance and you quickly exceed the speed of light. The most distant galaxies we've observed are more than 13 billion light-years away. The universe's expansion carries them away from us at speeds multiple times the speed of light. And they're not violating relativity, they're standing still in their own local space. It's the fabric of reality between us that's growing. This discovery reshaped our entire understanding of the cosmos. In 1929, Edwin Hubble first noticed that distant galaxies were moving away from us. He used what we now call the Hubble law, the relationship between a galaxy's distance and how fast it appears to recede. But he didn't yet know he was seeing the expansion of space itself. For decades, astronomers assumed the expansion was slowing down. Gravity should pull everything back together, right? But in 1998, 2 independent teams studying distant supernovae made a shocking discovery. The expansion wasn't slowing, it was speeding up. They won the Nobel Prize in Physics in 2011 for that discovery. And it introduced us to one of the deepest mysteries in science, dark energy. Whatever dark energy is, and we genuinely don't know, it makes up about 68% of everything in the universe, and it's pushing space apart faster and faster. Here's where the cosmic story gets even stranger. The expansion we measure nearby doesn't quite match the expansion we calculate from the early universe. Scientists call this the Hubble Tension. Recent measurements from the cosmic microwave background, light from when the universe was just 380,000 years old, suggest the expansion rate should be about 67.3 kilometers per second per megaparsec. But direct measurements of nearby galaxies consistently give us values around 73.5. That might not sound like a big difference, but it's statistically significant. It's been confirmed by multiple independent teams using different methods. Either we're making some systematic error we haven't identified, or something fundamental about our model of the universe is incomplete. If you're enjoying this cosmic journey, hitting that subscribe button and giving this video a like really helps. We're exploring the deepest questions about reality, and I want to bring you along for every discovery. Your support makes that possible. Now here's something most people don't realize. The expansion of space doesn't just affect distant galaxies, It's happening everywhere, even right here, even between you and me. But on small scales, human scales, planetary scales, even galactic scales, gravity is strong enough to hold things together. The atoms in your body aren't expanding. Earth isn't expanding. Even the Milky Way galaxy isn't expanding. Expansion only dominates at scales where gravity becomes too weak to resist it, roughly beyond groups of galaxies, at distances of tens of millions of light-years. Below that, local gravitational bonds win. Above that, the expansion of space takes over. This tells us something profound about the universe's structure. Reality is a dynamic interplay between forces trying to pull things together and the fundamental expansion trying to push them apart. We live in a universe balanced on that edge. The expansion also has consequences for the future. Right now, we can see galaxies up to about 46 billion light-years away in all directions. That's the observable universe, the sphere of space from which light has had time to reach us since the Big Bang. But as expansion accelerates, more and more galaxies will cross what's called the cosmic event horizon. Once they do, light leaving them will never reach us. Space between us expands faster than light can cross it. In the distant future, trillions of years from now, galaxies beyond our local group will have receded beyond that horizon. Any civilizations living then will look out at a dark, nearly empty universe. They'll see only their own galaxy and maybe a few neighbors. The rest of the cosmos will have disappeared from view, carried away by the expansion faster than light can travel. But the expansion of space is just the beginning of our faster-than-light story. There's something even more mind-bending, something that happened in the first fraction of a second after the Big Bang. We call it cosmic inflation. Imagine the entire observable universe, every galaxy, every star, every atom you can see in any direction was once smaller than a single atom. Then, in less time than it takes light to cross that atom, it exploded to the size of a grapefruit, or maybe even larger. That's inflation. This didn't happen slowly, this wasn't gradual expansion. In approximately 10 to the negative 36 seconds, that's a decimal point followed by 35 zeros and then a 1, the universe expanded by a factor of at least 10 to the 26. Some models suggest even more dramatic expansion. To put that in perspective, if you expanded a single atom by the same factor, it would be larger than our entire observable universe today. And this happened faster than anything we can properly comprehend. Space itself inflated at speeds vastly exceeding light. Now, you might be thinking this sounds like wild speculation, but inflation solves several profound mysteries about our universe that otherwise make no sense. Let me walk you through them. First, there's the horizon problem. When we look at the cosmic microwave background, the afterglow of the Big Bang, we see it's almost perfectly uniform in all directions. The temperature varies by only about 1 part in 100,000. That's remarkably smooth, but here's the puzzle. Regions of space on opposite sides of the observable universe have never been in contact with each other. Light from one side hasn't had time to reach the other side, even in the entire age of the universe. So how did they end up at the same temperature? It's like finding two people on opposite sides of Earth wearing identical, unique outfits without ever communicating. Something must have coordinated them. Inflation solves this beautifully. Before inflation, the entire observable universe was a tiny, connected region where everything could reach thermal equilibrium, the same temperature everywhere. Then, inflation stretched that tiny, uniform patch to cosmic scales. The uniformity we see today is the stretched-out imprint of that original tiny region. Second, there's the flatness problem. The universe's overall geometry, whether it curves back on itself like a sphere, curves outward like a saddle, or extends flat like an infinite sheet, depends on its density. Measurements tell us our universe is flat to incredible precision. But here's the thing. In the early universe, even tiny deviations from perfect flatness would have grown exponentially. For the universe to be as flat as we observe today, its initial density must have been fine-tuned to more than 60 decimal places. That's like balancing a pencil on its point and having it stay perfectly upright for billions of years. Inflation explains this too. Just like inflating a balloon makes its surface appear flatter, inflating the universe to enormous scales makes any initial curvature undetectable. Whatever curvature existed before, inflation got stretched out beyond what we can possibly observe. The evidence for inflation comes from multiple sources. The Planck satellite, which operated from 2013 to 2018, mapped the cosmic microwave background with unprecedented precision. The patterns it found, tiny temperature fluctuations that seeded galaxy formation, match exactly what inflation predicts. The Wilkinson Microwave Anisotropy Probe, or WMAP, which ran from 2001 to 2010, provided earlier confirmation. Ground-based observatories like the Atacama Cosmology Telescope and the South Pole Telescope have added supporting measurements. All of them point to the same conclusion. Something like inflation happened. In 2014, there was tremendous excitement when the BICEP 2 experiment announced they detected primordial gravitational waves from inflation, ripples in space-time itself, created during that explosive expansion. It would have been direct evidence, the smoking gun. But further analysis showed the signal was actually from dust in our own galaxy. The search continues. Still, inflation remains our best explanation for the universe's large-scale structure. And it requires space to expand faster than light, much, much faster than light, for a brief but crucial moment in cosmic history. Now let me take you to something completely different but equally fascinating. If you've been wondering about the limits of physical motion through space itself, I actually made a whole video exploring that question. It's called How Fast Can We Actually Move Through Space? And it dives deep into spacecraft propulsion, relativistic speeds, and what physics allows versus what engineering can achieve. The link of the video is in the description, but let's return to our faster-than-light phenomena. Because there's another one that sounds like pure science fiction but is absolutely real. It's called quantum entanglement. Here's how it works. You can create two particles, let's say photons, in such a way that their properties become linked, not just correlated, but fundamentally connected. When you measure one particle and find it spinning clockwise, the other particle instantly becomes counterclockwise no matter how far apart they are. And I mean instantly, not very quickly, not faster than we can measure. Actually genuinely instantaneous. Measure one particle on Earth, and its partner on the other side of the galaxy responds in the same moment. Zero time delay. Einstein called this spooky action at a distance, and he hated it. It seemed to violate everything relativity told us about the universe, but experiment after experiment has confirmed it's real. In 2015, physicists finally closed what's called the locality loophole. They proved beyond doubt that the correlation isn't due to hidden information carried by the particles. The connection is genuinely non-local. In 2017, Chinese scientists used the Messier satellite to demonstrate quantum entanglement between particles separated by over 1,200 kilometers. In 2022, the Nobel Prize in Physics went to 3 researchers who proved entanglement violates local realism, the idea that objects have definite properties independent of observation. Just this year, in 2026, multiple research teams published papers exploring quantum entanglement in cosmological contexts. One study examined how entanglement behaves in the expanding universe. Another investigated whether space-time curvature affects entangled particles. The research is ongoing and absolutely cutting edge. But here's the crucial detail. Entanglement doesn't let you send information faster than light. You can't use it for communication. When you measure your particle, you get a random result. The correlation only appears when you compare measurements afterward, which requires classical communication that travels at or below light speed. So entanglement is genuinely faster than light. The correlation happens instantaneously, but it can't violate causality. You can't use it to send a message to the past or signal faster than light. The universe protects itself from paradoxes. Still, the fact that this correlation exists, that particles separated by cosmic distances remain connected in this way, tells us something profound. The universe isn't made of isolated, independent pieces. There's a deeper level of connection we're only beginning to understand. Some physicists propose that entanglement might be related to the structure of space-time itself. There's a conjecture called ER equals EPR, Einstein-Rosen bridges equal Einstein-Podolsky-Rosen pairs. It suggests quantum entanglement might be equivalent to microscopic wormholes connecting entangled particles through space-time. It sounds wild, but serious theoretical work explores these ideas. Recent papers published just months ago examined how entanglement might encode information about the geometric structure of space. If they're right, the fabric of reality might literally be woven from quantum connections. Think about what that means. Every particle that's ever interacted remains connected at some level. The atoms in your body were forged in stars that exploded billions of years ago. Those atoms remain quantumly entangled with particles scattered across the galaxy. You're not separate from the cosmos. You're part of an interconnected web that spans space and time. Now let's talk about something that might surprise you. Light itself can appear to move faster than light. I know that sounds impossible, but hear me out. When we say light travels at the speed of light, we're talking about the speed of individual photons moving through a vacuum. That speed, approximately 299,792,458 meters per second, is constant and unchanging. But light waves are more complex than individual photons racing through space. A light wave has what physicists call a phase velocity and a group velocity. The phase velocity is how fast the wave's peaks and troughs move. The group velocity is how fast the actual energy and information travel. Usually, these are the same. But under special circumstances, they can differ dramatically. In April 2026, just weeks ago, researchers published a remarkable study in a leading physics journal. They observed something called optical vortices, essentially whirlpools of light, moving faster than the speed of light through a two-dimensional material. Let me explain what they saw. When light waves interact in certain materials, they can create points where the waves completely cancel each other out. These points of darkness form vortex structures like the eye of a hurricane but made of light, and these vortex centers can move through the material faster than light itself travels. Now, before you think this breaks physics, here's the key detail. These vortices carry no mass, no energy, and no information. They're patterns in the light field, not physical objects. Think of them like the spot where a pair of scissors blades meet. If you close very long scissors, that meeting point can slide along the blades faster than anything is actually moving. The point isn't a real object, it's a geometric feature. The researchers used an incredibly sophisticated electron microscope with unprecedented temporal and spatial resolution to capture these dynamics in real time. They developed a new interferometry method that enhanced image sharpness and allowed them to track the vortex motion with extraordinary precision. This breakthrough doesn't violate relativity because no actual information travels faster than light, but it reveals the rich complexity hidden in wave phenomena. It also opens possibilities for advanced microscopy techniques and helps us understand wave dynamics across diverse physical systems. Similar effects happen all the time in nature, just at different scales. You can see them in water waves, sound waves, even seismic waves traveling through Earth. The mathematics describing these phenomena applies universally, from quantum fields to classical waves to the structure of space-time itself. Speaking of which, there's another light-related phenomenon that deserves attention. It's called superluminal motion, and astronomers observe it regularly in jets shooting from black holes and neutron stars. Here's what happens. Some black holes and neutron stars generate enormous jets of material blasting outward at nearly the speed of light. When these jets point, almost, but not quite, directly toward Earth, they create an optical illusion. The material appears to move across the sky faster than light. The geometry creates this illusion beautifully. Imagine a jet racing toward you at 99% of light speed, tilted just slightly off your line of sight. The material at the front of the jet is almost keeping pace with the light it emits. So light emitted early in the jet's journey and light emitted later both reach you within a very short time interval. From your perspective, the jet appears to cross a certain distance in less time than light should take to cover that distance. But this is purely a projection effect. Nothing actually exceeds light speed. It's cosmic geometry playing tricks on our perception. Astronomers have observed this superluminal motion in numerous cosmic jets. The Very Long Baseline Array, a continent-spanning network of radio telescopes, has tracked apparent faster-than-light motion in jets from quasars billions of light-years away. The Event Horizon telescope, which gave us the first image of a black hole in 2019, has studied these jets in unprecedented detail. In 2017, astronomers observed a neutron star merger that produced gravitational waves detected by LIGO and Virgo. The merger also generated electromagnetic radiation across the spectrum, gamma rays, X-rays, visible light, radio waves, and it ejected material that created a superluminal jet. The observations were extraordinary. Multiple telescopes worldwide coordinated to track the event across different wavelengths. They measured the jet's apparent speed at several times the speed of light, but detailed analysis confirmed it was the projection effect. The actual material traveled at about 97% of light speed. These observations teach us something profound about extreme physics. Near black holes and neutron stars, matter gets accelerated to relativistic speeds, significant fractions of light speed. Time dilation kicks in, distances contract. The normal rules of everyday physics transform into something strange and counterintuitive. Particles in these jets experience time passing more slowly relative to us. If you could ride along with the jet material, the journey across the galaxy wouldn't take thousands of years from your perspective. It might take only years or even months. Your clock would tick slower. Your ruler would measure distances as shorter. This brings us to something fascinating about the nature of speed itself. Speed isn't absolute. It depends on your frame of reference. From Earth, that jet travels at 97% of light speed. But from the jet's perspective, it's stationary. Space flows past it. Einstein's relativity tells us there's no privileged reference frame, no absolute standard of rest. Every observer has an equally valid perspective. The universe doesn't have a universal clock or a universal measuring stick. Motion, distance, and time are relative to the observer. This might seem abstract, but it has real consequences. The Global Positioning System satellites orbiting Earth must account for relativistic time dilation. They travel fast enough and experience weak enough gravity compared to Earth's surface that their clocks tick at a different rate than ours. Without relativistic corrections, GPS would accumulate errors of kilometers per day. Particle accelerators like the Large Hadron Collider routinely accelerate protons to 99.999991% of light speed. At those speeds, time dilation is dramatic. Particles that would normally decay in microseconds survive for much longer because their internal clocks run slow relative to the laboratory. We've measured these effects countless times. They're not theoretical curiosities, they're engineering challenges we solve routinely. Relativity is as real and tested as any scientific theory in history, but relativity also sets firm limits. You can accelerate closer and closer to light speed, but you can never quite reach it. As you approach light speed, several things happen. Your mass effectively increases, making further acceleration harder. Time dilation becomes more extreme. Distances in your direction of travel contract. If you could somehow reach exactly light speed, which you can't, your mass would become infinite, time would stop entirely, and distances would shrink to zero. The math breaks down. Physics forbids it. Only massless particles like photons can travel at light speed, and they must always travel at exactly that speed. A photon never accelerates from rest. It's created moving at light speed and destroyed moving at light speed. From a photon's perspective, if it had one, no time passes during its journey. It's emitted and absorbed in the same instant, even if billions of years pass from our perspective. This is one of the beautiful mysteries of physics. The universe has this fundamental speed built into its structure. It's not just the speed of light. It's the speed of causality, the maximum rate at which cause can lead to effect, the cosmic speed limit for information and influence. And yet, as we've seen, the universe finds ways around this limit, not by violating it, but by operating on different levels. Space itself can expand faster than light. Quantum correlations can connect distant particles instantaneously. Geometric projections can create illusions of faster-than-light motion. The universe is far stranger and more subtle than simple rules would suggest. Every answer opens new questions. Every discovery reveals deeper mysteries. Let's dive deeper into one of the most bizarre implications of faster-than-light expansion. It's called the Cosmological Horizon, and it creates a boundary in space beyond which we can never see, no matter how long we wait or how powerful our telescopes become. Right now, the observable universe extends about 46.5 billion light-years in every direction. You might wonder why it's not 13.8 billion light-years, given that's the age of the universe. The answer is expansion. While light from distant galaxies traveled toward us, space itself stretched, carrying those galaxies farther away. But here's the mind-bending part. There are galaxies that exist right now, shining brightly, whose light will never reach us. Ever. Not in a trillion years? Not in a Google years? Not in infinite time? Why? Because the expansion of space between us and them exceeds the speed at which their light approaches us. Imagine you're on a treadmill running forward, but the treadmill moves backward faster than you can run. You make progress relative to the treadmill surface, but you move backward relative to the room. That's what happens to light from the most distant galaxies. This creates what physicists call the particle horizon, the boundary between regions from which light can eventually reach us and regions from which it cannot. It's not a physical barrier. There's nothing special about that location in space, but it represents a fundamental limit to what we can ever observe. And as the expansion accelerates, this horizon is actually shrinking in some sense. Galaxies that we can see today will eventually cross the horizon and disappear from view. Their light will become so redshifted, stretched to longer and longer wavelengths, that it becomes undetectable. They'll fade from visible light to infrared, to microwave, to radio waves, to wavelengths longer than our entire observable universe. Eventually, they'll vanish completely, not because they stopped existing, but because the space between us expanded so much that no signal can bridge the gap. Think about what this means for the far future. In several trillion years, the Milky Way and Andromeda will have merged into a single galaxy. The other members of our local galaxy group will have joined us. But beyond that, darkness. Every other galaxy in the universe will have receded beyond the cosmological horizon. Future astronomers living in that distant era will look out at a universe that appears to contain only their own galaxy, surrounded by empty space. They'll see no expansion because all the receding galaxies will have disappeared. They'll see a static, seemingly eternal universe. If they discover the cosmic microwave background, it will have redshifted to such long wavelengths and low temperatures that it might be undetectable. The evidence for the Big Bang might have faded away. Those future scientists might conclude they live in an unchanging cosmos, never realizing they inhabit an expanding universe with a beginning and probably an end. This is one of the most profound realizations in modern cosmology. We live in a special epoch. We can see the full richness of the universe, distant galaxies, the cosmic microwave background, the evidence for our cosmic origins. Future civilizations might not have that privilege. It makes you wonder what evidence might have already disappeared. What could civilizations living 1 trillion years in our past have observed that we can no longer see? Did the very early universe leave signatures that have now vanished beyond our reach? Some cosmologists take this idea seriously. Perhaps the universe underwent multiple phases we can't detect because the evidence has expanded away or decayed beyond recognition. Perhaps there were structures or phenomena in the first moments after the Big Bang that left no trace we can currently observe. This connects to another faster-than-light phenomenon, the recession of the cosmological horizon itself. The boundary of what we can observe isn't static. It changes as the universe expands and as time passes. In some models of cosmic expansion, this horizon recedes at speeds exceeding light. But let's shift gears to something equally fascinating and far more violent. Let's talk about gamma-ray bursts. Gamma-ray bursts are the brightest electromagnetic events in the universe. For a few seconds to a few minutes, a single gamma-ray burst can outshine the entire rest of the universe in gamma-ray light. They release as much energy in seconds as our Sun will emit over its entire 10 billion-year lifetime. These cosmic explosions happen when massive stars collapse into black holes or when neutron stars collide. The collapsing or colliding objects generate jets of material and radiation blasting outward at 99.9% of light speed or faster. Wait, faster? Yes, but we need to be precise about what that means. The material in these jets travels at extremely relativistic speeds, right at the edge of what physics allows. When particles in the jet interact with surrounding gas and dust, they create shock waves. These shock waves can propagate through the material faster than light travels through that same material. Let me explain. Light slows down when traveling through anything other than vacuum. In water, light travels at about 75% of its vacuum speed. In glass, it's even slower. In exotic materials, scientists have slowed light to walking pace or even brought it to a complete stop. When a shock wave moves through material faster than light moves through that material, something remarkable happens. It's called a photonic boom, analogous to a sonic boom when an aircraft exceeds the speed of sound. The shock wave creates a distinctive pattern of radiation. In gamma-ray burst jets, the shock waves generate this effect at cosmic scales. The interaction produces the intense gamma radiation we detect. Different parts of the jet moving at slightly different speeds create complex interference patterns. The radiation flickers and fluctuates in ways that encode information about the jet's structure and speed. Astronomers have studied hundreds of gamma-ray bursts since their discovery in the 1960s. The SWIFT satellite, launched in 2004, detects several bursts per week. The Fermi Gamma-Ray Space Telescope, operating since 2008, has observed thousands of these events. Each gamma-ray burst tells a story of cosmic catastrophe. Each one marks the death of a massive star or the merger of compact objects. Each one briefly becomes the brightest beacon in its region of the universe, and we can detect them from billions of light-years away. In 2022, astronomers observed the brightest gamma-ray burst ever recorded. They nicknamed it the Boat, the brightest of all time. It originated from a galaxy 2.4 billion light-years away and was so intense that it temporarily blinded gamma-ray detectors across the solar system. The boat was so bright that it ionized Earth's upper atmosphere. It created measurable effects on our planet's magnetic field. An event that happened 2.4 billion light-years away physically influenced Earth's environment. That gives you a sense of the energy scales involved. These explosions also produce gravitational waves, ripples in space-time itself, predicted by Einstein and first detected in 2015. When neutron stars collide, they generate both gamma-ray bursts and gravitational waves. By detecting both signals, astronomers can study the same event through completely different channels. In 2017, the LIGO and Virgo gravitational wave detectors observed a neutron star merger just seconds before gamma-ray satellites detected the corresponding burst. It was the first time we observed the same cosmic event in both gravitational waves and electromagnetic radiation. This observation confirmed something remarkable. Gravitational waves travel at exactly the speed of light, not almost. Exactly. The gravitational wave signal and the gamma-ray signal, traveling across 130 million light-years of space, arrived within just seconds of each other. This confirmed predictions from general relativity to extraordinary precision. It also ruled out certain alternative theories of gravity that predicted gravitational waves should travel at different speeds. One observation eliminated entire classes of theoretical models. The precision of that measurement, gravitational waves traveling at the speed of light across 130 million light-years, reveals something profound about the universe's consistency. Physical laws don't change from place to place. The speed of light measured here matches the speed measured in galaxies billions of light-years away. The universe operates on principles we can rely on. But let's explore something that challenges our intuitions even further. There's a phenomenon called Cherenkov radiation that involves particles moving faster than light. Yes, you heard that correctly. Here's how it works. Remember, I mentioned that light slows down in materials? In water, light travels at about 225 million meters per second instead of 300 million, but particles can still move faster than this reduced speed while staying below the universal light speed limit in vacuum. When a charged particle moves through a material faster than light moves through that material, it creates a shock wave of electromagnetic radiation. This is Cherenkov radiation, and it produces a characteristic blue glow. You can see this effect in nuclear reactors. The spent fuel rods stored in cooling pools emit an eerie blue light. That's Cherenkov radiation from electrons moving through water faster than light moves through water. Those electrons aren't violating relativity, they're just moving faster than light's reduced speed in the medium. It's exactly analogous to a sonic boom. When an aircraft exceeds the speed of sound in air, it creates a shock wave. When a particle exceeds the speed of light in a medium, it creates an electromagnetic shock wave. Scientists use this principle in particle detectors. Large underground laboratories like Superluminal in Japan use tanks filled with ultra-pure water surrounded by thousands of light sensors. When neutrinos, ghostly particles that barely interact with matter, occasionally collide with atoms in the water, they produce charged particles that generate Cherenkov light. The detectors capture these brief flashes and reconstruct what happened. In 2020, the Superluminal detector began an upgrade called Superluminal gadolinium, adding gadolinium to the water to enhance neutron detection. This improves sensitivity to neutrinos from supernovae and other cosmic sources. The IceCube Neutrino Observatory at the South Pole uses a cubic kilometer of Antarctic ice as a Cherenkov detector, making it one of the largest scientific instruments ever built. IceCube detects neutrinos from the most violent events in the universe, supernovae, gamma-ray bursts, and the regions around supermassive black holes. In 2013, IceCube detected the first high-energy neutrinos from beyond our solar system. In 2017, it traced a neutrino back to a blazar, a galaxy with a supermassive black hole jet pointing directly at Earth 4 billion light-years away. That detection opened a new window on the universe. We now do astronomy not just with light and gravitational waves, but with neutrinos. We're seeing the cosmos through three fundamentally different messengers, each revealing phenomena the others cannot. And all of this depends on particles moving faster than the local speed of light in a medium, creating detectable radiation through the Cherenkov effect. Now, let me take you to something that exists purely in mathematics but tells us something deep about reality. It's called tachyons. Tachyons are hypothetical particles that always move faster than light, not approaching light speed from below but existing permanently above it. If tachyons exist, they would have imaginary mass that involves the square root of -1. I know that sounds absurd, and honestly, most physicists think tachyons probably don't exist. We've never detected one. They create bizarre causality problems, potential paradoxes where effects could precede causes. But here's the interesting part. Tachyons appear naturally in certain equations of theoretical physics. In some versions of string theory, tachyons emerge as instabilities in the mathematical structure. Their presence signals that the theory is in an unstable state, trying to decay to something more stable. Think of tachyons like a ball balanced on top of a hill. The balance position is mathematically possible but physically unstable. Any tiny perturbation sends the ball rolling downward toward a stable valley. Tachyons in string theory work similarly. They indicate the theory needs to settle into a different, more stable configuration. Some physicists have explored whether tachyons could exist in ways that don't violate causality. Perhaps they can only be created and destroyed in specific configurations that prevent paradoxes. Perhaps they exist in extra dimensions we can't directly access. Perhaps they're purely mathematical artifacts with no physical reality. The jury is still out. But the fact that faster-than-light particles appear in our best mathematical descriptions of nature suggests something interesting. Either we haven't fully understood those mathematical descriptions, or the universe has possibilities we haven't yet observed. Let me bring us back to something more concrete and absolutely confirmed: the quantum vacuum. You might think empty space is truly empty, containing nothing at all. But quantum mechanics says otherwise. Even in the deepest vacuum, devoid of matter and radiation, quantum fields fluctuate. Virtual particles pop in and out of existence, borrowing energy from the vacuum for impossibly brief moments before annihilating. These aren't just mathematical abstractions. These quantum fluctuations have measurable effects. They create a force called the Casimir effect, where two metal plates placed extremely close together in vacuum experience an attractive force because the quantum fluctuations between the plates differ from those outside. Physicists have measured the Casimir force in laboratories. It matches quantum field theory predictions precisely. The vacuum isn't empty, it seethes with quantum activity. Now here's where it gets strange. Some of these quantum vacuum fluctuations involve particles briefly traveling faster than light, or across distances instantaneously through quantum tunneling. They exist only for time intervals so short that Heisenberg's uncertainty principle allows energy conservation to be violated temporarily. It's like the universe running a deficit budget, borrowing energy it doesn't have as long as it pays everything back before anyone can definitively measure the violation. The more energy you borrow, the faster you must pay it back. Borrow enough energy to create particle-antiparticle pairs, and they must annihilate in less than 10 to the negative 23 seconds. These processes happen everywhere, constantly. Right now, in the space between your eyes and this screen, countless virtual particles are appearing and disappearing. The quantum vacuum surrounding you fluctuates with unimaginable complexity. Some theoretical physicists propose that these quantum vacuum fluctuations might relate to dark energy, the mysterious force accelerating cosmic expansion. Perhaps the energy density of the vacuum itself drives the expansion. There's a problem, though. When physicists calculate the vacuum energy density from quantum field theory, they get an answer that's off by about 120 orders of magnitude, a 1 followed by 120 zeros. It's possibly the worst prediction in the history of physics. Either the calculation is profoundly wrong in ways we don't understand, or there's some cancellation mechanism we haven't discovered that reduces the vacuum energy to the tiny value we observe. This is called the cosmological constant problem, and it's one of the deepest puzzles in theoretical physics. Understanding the quantum vacuum might require a complete theory of quantum gravity, a framework that unites general relativity and quantum mechanics. We don't have that theory yet. String theory, loop quantum gravity, and other approaches attempt to provide it, but none have been experimentally confirmed. This brings us to a humbling realization. Despite everything we've learned about the universe, despite all our telescopes and particle accelerators and mathematical sophistication, we still don't understand what makes up most of reality. Dark energy constitutes about 68% of the universe. Dark matter makes up about 27%. Normal matter, atoms, the stuff we're made of, accounts for less than 5%. We don't know what dark energy is. We don't know what dark matter is. We can detect their effects, but their fundamental nature remains mysterious. And some of the fastest phenomena in the universe, the expansion driven by dark energy, the dynamics of dark matter, halos around galaxies, involve things we cannot directly observe. We see their consequences, we measure their influences, but the substances themselves remain hidden. Dark matter presents one of the greatest mysteries in modern astrophysics, and its behavior involves speeds and dynamics that challenge our understanding. Let me paint you a picture of what we know. Galaxies rotate. Stars orbit around galactic centers, held in place by gravity. When astronomers measure how fast stars move at different distances from a galaxy's center, they can calculate how much mass the galaxy contains and where that mass is distributed. Here's the problem. Stars at the edges of galaxies move way too fast. According to the visible matter we can see, stars, gas clouds, dust, those outer stars should be moving much slower, or they should fly off into intergalactic space, but they don't. They orbit steadily, held by gravity from matter we cannot see. Vera Rubin made these observations in the 1970s, though hints of the problem existed earlier. She measured rotation curves for dozens of galaxies and found the same pattern everywhere. The visible matter couldn't explain the gravitational effects. Something invisible, something that doesn't emit or absorb light, must be providing the extra gravity. We call this substance dark matter. It doesn't interact with electromagnetic radiation. No light, no radio waves, no X-rays. It responds only to gravity and possibly to the weak nuclear force. It passes through normal matter like a ghost, and there's a lot of it. About 5 times more dark matter than normal matter fills the universe. Every galaxy sits embedded in a massive halo of dark matter, extending far beyond the visible stars. These halos can be 10 times larger than the galaxies themselves. Dark matter moves. It flows through and around galaxies. Computer simulations show how dark matter collapses under gravity, forming cosmic web structures, filaments and nodes where galaxies form. These simulations match observations beautifully when they include dark matter. Without it, they fail completely. Some of this dark matter moves at incredible speeds. Computer models suggest dark matter particles in galactic halos can reach velocities of several hundred kilometers per second. In galaxy cluster collisions, dark matter can move even faster. The Bullet Cluster provides spectacular evidence for dark matter. It's actually two galaxy clusters that collided billions of years ago. When astronomers observe the Bullet Cluster, they see something remarkable. The normal matter, hot gas between galaxies, interacted during the collision. The gas from each cluster slammed into the gas from the other cluster, slowing down through electromagnetic forces. The gas now sits in the middle between the clusters, but the dark matter passed right through. It experienced only gravity, which is far weaker than electromagnetic forces. The dark matter halos from each cluster passed through each other like ghosts, emerging on opposite sides of the collision. We can map where the dark matter is using gravitational lensing. Massive objects bend space-time, causing light from background galaxies to curve around them. By measuring this distortion, astronomers can map the mass distribution, including invisible dark matter. In the Bullet Cluster, the gravitational lensing reveals that most of the mass, the dark matter, is separated from the normal matter. This observation, made in 2006, provided some of the strongest evidence that dark matter is real, not just a modification to gravity. Think about what happened there. Two enormous clusters, each containing hundreds of galaxies and vast quantities of dark matter, collided at speeds of millions of kilometers per hour. The normal matter crashed and piled up. The dark matter sailed right through, barely noticing the collision. Multiple experiments worldwide hunt for dark matter particles. The Large Hadron Collider searches for dark matter by trying to create it in high-energy collisions. Deep underground laboratories like Xenon, Lux Zeppelin, and Panda X look for rare events where dark matter particles might collide with detector atoms. So far, despite decades of searching, we haven't definitively detected a dark matter particle. We see its gravitational effects everywhere, in galaxies, galaxy clusters, gravitational lensing, the cosmic microwave background. But the particle itself remains elusive. Some physicists propose alternatives. Maybe we don't need dark matter at all. Maybe gravity works differently than general relativity predicts on galactic scales. Modified Newtonian dynamics, or MOND, attempts this approach. But MOND struggles to explain observations like the Bullet Cluster. It can't easily account for gravitational lensing measurements. It requires different modifications in different contexts. Dark matter, despite being mysterious and undetected, explains more observations with fewer assumptions. Recent observations make the picture even more interesting. In 2023, astronomers studying ultra-diffuse galaxies, galaxies with very few stars spread over large areas, found some that appear to contain almost no dark matter. Others contain normal amounts. This suggests dark matter and normal matter can separate under certain conditions. If we're right about dark matter, it's flowing through you right now. Thousands, maybe millions of dark matter particles pass through your body every second. They interact so weakly that they slide through atoms like those atoms weren't even there. You don't feel them, they don't affect you, they're just passing through on their journey through the galaxy. The Milky Way moves through space at over 2 million kilometers per hour relative to the cosmic microwave background. We orbit the galactic center at about 790,000 kilometers per hour. The solar system bobs up and down through the galactic plane. All of this motion carries us through the dark matter halo surrounding our galaxy. Scientists call this the dark matter wind, our motion through the background sea of dark matter particles. Some detection experiments account for this wind, looking for directional signals that change as Earth orbits the Sun and our orientation to the galactic center shifts. Now let me take you even deeper into the cosmic speed hierarchy. Let's talk about the fastest natural accelerators in the universe, the environments around black holes and neutron stars. Black holes are regions where space-time curves so extremely that nothing, not even light, can escape from within the event horizon. But just outside the event horizon, in the region called the ergosphere, space-time itself gets dragged around the spinning black hole. This effect, called frame dragging, means that nothing can remain stationary relative to distant space. Everything, matter, light, even the fabric of space-time, gets pulled along in the black hole's rotation. Near rapidly spinning black holes, this dragging can approach light speed. Material falling toward a black hole doesn't fall straight in. It forms an accretion disk, a swirling maelstrom of superheated gas, spiraling inward. Friction within the disk heats material to millions of degrees. The inner edge of the disk, just outside the event horizon, orbits at significant fractions of light speed. For a stellar mass black hole, one formed from a collapsed star, the innermost stable circular orbit sits just a few kilometers from the event horizon. Material orbiting there completes circuits in milliseconds, traveling at 30 to 40% of light speed. For supermassive black holes like Sagittarius A star at the center of our galaxy, the scales are larger, but the speeds remain comparable. The Event Horizon Telescope imaged Sagittarius A star in 2022, revealing the shadow of the event horizon surrounded by a bright ring of emission from the accretion disk. That bright ring comes from material orbiting at relativistic speeds, heated to billions of degrees. Magnetic fields threading through the disk twist and snap, accelerating particles to extraordinary energies. Some particles get launched away in jets perpendicular to the disk, shooting outward at 99% of light speed or faster. These jets can extend for millions of light years, spanning distances larger than entire galaxy clusters. The jets from the supermassive black hole in the galaxy M87 stretch for about 100,000 light-years. The jets from radio galaxies like Centaurus A extend even farther. How do black holes generate such powerful outflows? The exact mechanisms remain debated, but the basic picture involves the interaction between the accretion disk, magnetic fields, and the black hole's rotation. The mechanism powering these jets involves some of the most extreme physics imaginable. Roger Penrose proposed one process in 1969, now called the Penrose process. It exploits the rotational energy of the black hole itself. Here's how it works conceptually. In the ergosphere, the region just outside the event horizon where space-time is dragged along with the black hole's rotation, particle trajectories can have negative energy relative to distant observers. If a particle splits into two fragments in this region, and one fragment falls into the black hole while the other escapes, the escaping fragment can carry away more energy than the original particle had. This isn't magic. The fragment that fell into the black hole had negative energy, so it actually reduced the black hole's mass and rotation. Energy is conserved, but from our perspective, we extracted energy from the black hole's rotation and transferred it to the escaping particle. The Blandford-Znajek process, proposed in 1977, extends this idea using magnetic fields. Magnetic field lines threading through the ergosphere get twisted by the black hole's rotation. This twisting builds up electromagnetic energy, which eventually gets released as jets of particles and radiation blasting away at relativistic speeds. Computer simulations of this process have become extraordinarily sophisticated. In 2025, researchers published simulations that track the dynamics of plasma around spinning black holes with unprecedented resolution. They showed how magnetic field lines snap and reconnect, how particles get accelerated, how the jets form and maintain their structure across vast distances. These simulations require some of the world's most powerful supercomputers. They solve Einstein's equations of general relativity simultaneously with Maxwell's equations of electromagnetism, while tracking the motion of plasma flows in extreme gravitational and magnetic environments. The computational demands are staggering, but the results match observations beautifully. The simulations predict jet speeds, brightness patterns, variability timescales, and polarization properties that agree with what telescopes see. This gives us confidence that we're understanding the basic physics correctly, even if many details remain unclear. Neutron stars provide another extreme environment for particle acceleration. These are the collapsed cores of massive stars, packed so densely that protons and electrons merge into neutrons. A neutron star packs more mass than our Sun into a sphere just 20 kilometers across. Neutron stars spin. Some spin hundreds of times per second, completing rotations faster than a kitchen blender. These millisecond pulsars are the most stable clocks in the universe, their rotation rates constant to 15 decimal places. The surface of a spinning neutron star moves at significant fractions of light speed. A neutron star spinning at 700 rotations per second with a radius of 12 kilometers has surface velocity at the equator of about 26,000 kilometers per second, nearly 9% of light speed. And neutron stars have the strongest magnetic fields known in the universe. Regular neutron stars have fields of about 100 million to 1 trillion Tesla. Magnetars, a special class of highly magnetized neutron stars, have fields reaching 100 billion Tesla or more. For comparison, the strongest continuous magnetic fields produced in laboratories reach about 45 Tesla. The strongest pulsed fields, lasting just microseconds, approach a few thousand Tesla. Magnetar fields are billions of times stronger. These fields twist and stress the neutron star's crust. When the crust fractures, a starquake, the magnetic field reconfigures violently, releasing enormous bursts of energy. In December 2004, a magnetar called SGR 1806-20 produced a flare so intense that it affected Earth's ionosphere from 40,000 light-years away. That flare released more energy in 1/10 of a second than our Sun emits in 100,000 years. It briefly outshone the entire galaxy in gamma rays and X-rays. If it had occurred within 10 light-years of Earth, it might have caused a mass extinction. Magnetars also accelerate particles to incredible energies. The combination of rapid rotation and intense magnetic fields creates electric potentials of quadrillions of volts. Particles caught in these fields get accelerated to energies matching the most powerful cosmic rays. This brings us to cosmic rays themselves, one of the great ongoing mysteries in astrophysics. Cosmic rays are high-energy particles, mostly protons, that bombard Earth constantly from space. They were discovered in 1912 by Victor Hess during balloon flights. He noticed that radiation levels increased with altitude, indicating a source beyond Earth. Most cosmic rays have energies comparable to particles in the Large Hadron Collider, billions of electron volts, but some have far higher energies. The highest energy cosmic rays reach beyond 100 million trillion electron volts. These are the most energetic individual particles ever detected. Think about that. A single proton carrying the kinetic energy of a baseball pitched at 100 kilometers per hour. One atomic nucleus with enough energy that you could feel it if it hit you. These ultra-high energy cosmic rays arrive rarely, about 1 per square kilometer per century, but they exist. Where do they come from? What natural process can accelerate individual particles to such extraordinary energies? This question has puzzled physicists for decades. Supernova remnants can accelerate particles to high energies through a process called Fermi acceleration. Shock waves from the explosion bounce particles back and forth, incrementally boosting their energy with each reflection. This explains cosmic rays up to about 1,000 trillion electron volts. But the highest energy cosmic rays require something more powerful. Galaxy clusters, with their colliding gas clouds and vast magnetic fields, might accelerate particles to higher energies. Active galactic nuclei, supermassive black holes accreting matter, could also contribute. The Pierre Auger Observatory in Argentina, which covers 3,000 square kilometers, studies these ultra-high energy cosmic rays. In 2017, researchers there published evidence that the highest energy cosmic rays come preferentially from directions outside our galaxy, supporting the idea that active galactic nuclei might be the source. But we still don't know for certain. The particles travel through magnetic fields in intergalactic space, which deflect their paths. By the time they arrive, their trajectories don't point directly back to their sources. Unraveling their origins requires careful statistical analysis and comparison with catalogues of potential source objects. When ultra-high energy cosmic rays hit Earth's atmosphere, they create particle cascades called air showers. A single incoming cosmic ray can generate billions of secondary particles spreading over several square kilometers. These air showers produce brief flashes of fluorescence light and particle detectors on the ground. The Pierre Auger Observatory uses both detection methods, arrays of ground detectors and telescopes watching for fluorescence flashes in the night sky. By combining these observations, researchers can reconstruct the energy, arrival direction, and composition of the original cosmic ray. In 2021, the Telescope Array in Utah, another large cosmic ray observatory, reported an excess of cosmic rays from a particular region of the sky. This hotspot suggests a nearby source might be preferentially accelerating particles in our direction, but the source hasn't been definitively identified. Some ultra-high energy cosmic rays arrive with energies that create a theoretical puzzle. There's a limit called the GZK cutoff, predicted in 1966. Cosmic rays with energies above this limit should interact with photons in the cosmic microwave background, losing energy and creating a natural upper limit. And indeed, we see a suppression of cosmic rays at the highest energies, consistent with the GZK cutoff. But some particles appear to exceed even this limit, suggesting they might originate from relatively nearby sources within about 100 million light-years, so they don't travel far enough through the cosmic microwave background to lose significant energy. This implies powerful particle accelerators exist within our cosmic neighborhood. Centaurus A, a galaxy with an active nucleus and prominent jets just 13 million light-years away, is a prime candidate. The Auger Observatory has detected hints of cosmic rays arriving from that direction. These particles race across millions of light-years at very nearly the speed of light. A cosmic ray traveling from Centaurus A to Earth at 99.9999999% of light speed would experience time dilation so extreme that the journey, from the particle's perspective, might take only seconds or minutes. From the particle's viewpoint, space itself contracts. The 13 million light-years shrink to perhaps a few light-years or less. What we measure as a journey lasting millions of years occupies just a brief moment for the particle itself. This is the profound strangeness of relativity. Time and space aren't absolute, they're flexible, observer-dependent. Every particle, every observer has its own valid perspective on reality. This relativity of time and space creates paradoxes that seem impossible but are absolutely real. Consider the twin paradox, a classic thought experiment that illustrates time dilation. Imagine two twins. One stays on Earth while the other boards a spaceship traveling at 99% of light speed to a distant star 10 light-years away and returns. From Earth's perspective, the journey takes about 20 years, but for the traveling twin, time passes much slower due to time dilation. When they reunite, the traveling twin might have aged only 3 years while the Earthbound twin aged 20. This isn't hypothetical. We've confirmed time dilation countless times with atomic clocks on airplanes, satellites, and particle accelerators. GPS satellites must account for relativistic time dilation, or they'd accumulate errors of kilometers per day. The clocks on those satellites run slightly faster than clocks on Earth's surface because they're in weaker gravity and moving at different speeds. Every time you use GPS navigation, you're relying on corrections derived from Einstein's relativity. Your phone triangulates your position using signals from satellites whose clocks tick at different rates than ground-based clocks. The system works only because engineers programmed in the relativistic corrections. Muons provide another beautiful demonstration. These particles are created when cosmic rays hit the upper atmosphere. Muons are unstable, decaying with a half-life of about 2 microseconds. At light speed, a muon should travel only about 600 meters before half of them decay. But muons created 20 kilometers up in the atmosphere reach Earth's surface in abundance. Why? Because they're moving at 99.9% of light speed, experiencing extreme time dilation. What takes 20 microseconds from our perspective might be only 2 microseconds from the muon's perspective. From the muon's viewpoint, the atmosphere is contracted to less than 1 kilometer thick. Both perspectives are correct. We see the muons living longer due to time dilation. The muons experience traveling through a compressed atmosphere. Different observers, same reality, different descriptions. Now let's push this further. What happens at the very edge of the speed limit? As particles approach light speed, strange things happen. When you accelerate a particle, you add energy. At low speeds, this energy goes into increasing velocity. But as you approach light speed, additional energy increasingly goes into increasing the particle's relativistic mass rather than its velocity. The closer you get to light speed, the more energy you need for each incremental increase in velocity. At 90% of light speed, doubling your energy doesn't double your speed, it only inches you closer to light speed. At 99%, you might need 10 times more energy to reach 99.9%. This is why the Large Hadron Collider is so enormous. It accelerates protons to 99.999991% of light speed. Those protons have been accelerated so much that their energy is about 7,000 times their rest mass. Most of their energy is kinetic, not intrinsic mass. Accelerating them to that speed requires 16.6 kilometers of superconducting magnets operating at temperatures colder than deep space, powered by enormous amounts of electricity. And even with all that infrastructure, the protons still fall short of light speed by about 3 meters per second. Imagine a spaceship traveling at 90% of light speed. It turns on a headlight. You might think the light should travel at 1.9 times light speed, 90% from the ship's motion plus 100% from the light itself. But it doesn't. The light travels at exactly light speed, no faster. This seems impossible, but it's how the universe works. Velocities don't add linearly at relativistic speeds. Time and space adjust to keep light speed constant for all observers. This constancy of light speed underlies all of special relativity. From this single principle, combined with the principle that physical laws are the same in all inertial reference frames, Einstein derived time dilation, length contraction, mass-energy equivalence, and the relativity of simultaneity. Events that appear simultaneous to one observer might occur at different times for another observer in motion. Time itself is relative. There's no universal now extending across the universe. Your present is not the same as the present of someone moving relative to you. This has profound implications. Consider a distant alien civilization 100 light-years away. If they're at rest relative to us, we might say events happening now on their planet are simultaneous with events now on Earth. But if they're moving toward us at high speed, their now might include events in Earth's past. If they're moving away, their now might include events in Earth's future. The notion of simultaneity becomes observer-dependent. There's no objective answer to what is happening right now across the universe. Different observers can disagree and all be correct within their reference frames. This makes faster-than-light travel deeply problematic for causality. If you could send a signal faster than light, you could send it into someone's past. Combined with their motion, this could create closed time-like curves, paths through space-time that loop back to their starting point. You could, in principle, send a message to yourself before you sent it. You could tell yourself not to send the message, creating a paradox. This is why most physicists believe faster-than-light communication is impossible. Not just technologically difficult, but fundamentally incompatible with causality. However, quantum mechanics introduces something peculiar called quantum entanglement that seems to involve faster-than-light correlations. When two particles are entangled, measuring one instantly affects the other, regardless of distance. Einstein called this spooky action at a distance and thought it revealed an incompleteness in quantum mechanics. He was wrong. Experiments have repeatedly confirmed quantum entanglement. In 2015, a loophole-free Bell test conclusively demonstrated that quantum mechanics correctly predicts correlations that no local hidden variable theory can explain. The particles really are instantaneously correlated across arbitrarily large distances. But here's the catch: you can't use entanglement to send information faster than light. The correlations are random until you measure both particles and compare results. The comparison requires classical communication, which is limited to light speed. It's like having two coins that always land on opposite sides. If you flip one in Tokyo and I flip one in New York, and yours shows heads, I can be certain mine shows tails instantly, but I don't know what mine shows until I look. And you can't control whether yours shows heads or tails, so we can't use this for communication. Quantum entanglement creates correlations, not causation. Information still cannot travel faster than light. Causality is preserved. Recently, physicists have explored whether quantum entanglement might help explain the interior structure of black holes and the nature of space-time itself. The ER-EPR conjecture, proposed in 2013, suggests that entangled particles might be connected by microscopic wormholes, Einstein-Rosen bridges. If true, this would link quantum entanglement with the geometry of space-time in profound ways. It might help resolve the black hole information paradox, which asks what happens to information that falls into a black hole. Does it disappear, violating quantum mechanics? Does it get preserved somehow? Stephen Hawking showed in the 1970s that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation carries energy away, causing black holes to slowly evaporate. Over immense timescales, even supermassive black holes will completely evaporate. But Hawking radiation appears to be random, carrying no information about what fell in. This conflicts with quantum mechanics, which says information cannot be destroyed. This is the information paradox. Recent work suggests that subtle correlations in Hawking radiation might preserve information after all, but in ways that require understanding the quantum structure of space-time itself. Some proposals involve information being encoded on the event horizon or released in the final moments of black hole evaporation. These questions push the boundaries of current physics. We need a complete theory of quantum gravity to answer them definitively. String theory, loop quantum gravity, and other approaches attempt this, but none have been experimentally confirmed. The speeds we've discussed, cosmic expansion, particle jets, gravitational waves, quantum correlations, all probe these fundamental limits. By studying the fastest phenomena in nature, we're probing the deepest questions about reality. What is space-time? Why does light have the speed it does? What determines the fundamental constants of nature? Why does the universe have the structure it does? These aren't just academic curiosities. Understanding these principles might enable technologies we can barely imagine. Mastery of space-time geometry could revolutionize transportation. Understanding quantum entanglement has already enabled quantum computing and quantum cryptography. Harnessing vacuum energy, if possible, would provide limitless power. If you made this far, make sure to give this video a like and make sure to subscribe. You don't want to miss what's coming next in the channel. And the video at the left side of the screen explores why we will never meet an alien civilization. See you there.